If you've ever looked up, at the night sky and spotted that bright reddish star, Arcturus, have you ever stopped to wonder about its journey?
Where's it really going?
Exactly. Is it just out there on its own,
Hmm?
or is it part of something bigger, something moving together through space?
And that question, it really gets right to the heart of what we're exploring today.
Hmm.
Because those stars, even the familiar ones, right here in our corner of the galaxy,
Uh-huh.
they have these incredible stories kind of encoded in their motion. They're often not just, randomly drifting.
Right.
They're part of these dynamic structures, these cosmic currents flowing through space.
Exactly. And
Yeah.
that's precisely what we're diving into today. Something astronomers call kinematic groups or star streams right here in our solar neighborhood.
Yeah.
Think of them like ancient rivers of stars, all sharing a common path. And, well, their motion whispers secrets about the Milky Way's deep past.
It's fascinating stuff. And the study of these stellar groupings, it really began with pioneers like Olin Eggen decades ago.
Right, Egan.
His initial idea was that these groups were simply the remnants of star clusters, collections of stars born together that were slowly dissolving or evaporating into the galaxy.
And that idea, it made sense at the time, but our understanding has been completely revolutionized.
Oh, absolutely.
Why?
Yeah.
Because of the Gaia Space Telescope. This mission has been an absolute game changer.
Couldn't agree more.
It's given us this unprecedented high-precision data.
Yeah.
It's allowed us to map stars' movements with incredible accuracy and, in doing so, completely rewrite our understanding of where these streams truly come from.
Yeah, with Gaia's really detailed measurements, we can finally look beyond just simple positions and speeds. We can understand the complex orbital paths that reveal a star's history.
So in this deep dive, we're going to unpack two specific examples from the material we looked at. The famous Arcturus stream.
The big one?
Yeah. That bright star you might see tonight is part of it. And also the HR 1614 group. We'll see how Gaia data has helped solve some long-standing mysteries about them.
And maybe more importantly, what they tell us about the turbulent dynamic history of our own galaxy.
Let's do it.
Okay, so first off, let's define exactly what we mean by star streams or kinematic groups.
Good idea.
These are groups of stars, often relatively close to our sun, maybe within a few thousand light years,
Yeah.
that share very similar motions. Astronomers describe this as having coherent kinematics.
Coherent kinematics. So they're all headed roughly in the same direction at a similar speed, moving together like a team.
Precisely. And what makes them stand out is that their motions are distinctly different from the average stars surrounding them. They often have what we call peculiar velocities. Their speeds are significantly higher or maybe in a different direction than the bulk motion of other stars of similar age in the area. They're sort of like outliers in the local stellar velocity distribution.
Okay, that makes sense. They stick out dynamically. So going back to Egan's original idea that some are evaporating clusters, is that ever true?
Oh, yes, absolutely. Gaia data clearly shows that some kinematic groups are indeed the dissolving remnants of star clusters.
Okay.
We see clear structures associated with clusters like the Hyades or the Pleiades, those famous nearby ones, and even the tidal tail of a more distant cluster like Palomar 5. It's beautifully traced out by Gaia.
Wow. But the sources we looked at make it clear that, especially for older groups, that's often not the primary explanation anymore.
That's right. Gaia data has revealed, or at least clarified, other major origins for these streams.
Okay, so what are they? What else makes these streams?
Well, one major source is the tidal debris from smaller satellite galaxies that the Milky Way has accreted.
Accreted.
Yeah.
Like gravitationally eaten over billions of years.
Exactly. Eaten is a good word for it. As these smaller galaxies fall into our larger one, our gravity tears them apart, scattering their stars into long, thin streams, often in the galactic halo or even crossing into the disk.
Like leftovers from galactic collisions.
Pretty much. The Helmi stream is a classic example, and Gaia has helped map many more, like streams associated with the Gaia Enceladus's merger event. That was a big one.
Incredible. So cosmic wreckage. What else can create these streams?
Another key mechanism involves the internal dynamics of the Milky Way itself. Features like the galaxy's central rotating bar,
Right, the bar structure in the middle.
its prominent spiral arms. They exert gravitational forces that can trap or influence the orbits of stars. These can create resonant features.
Resonant features.
Yeah, regions where stars with certain orbital properties tend to collect, forming coherent groups or streams. The Hercules stream, which we've actually talked about before,
Oh, yeah,
I remember, is considered a prime example of this kind of resonant origin. likely linked to the bar's rotation speed.
And the sources mentioned even more possibilities, like phase mixing or something.
Exactly, phase mixing. It's a bit complex, but imagine stars get stirred up, maybe by a dissolving spiral arm, or even an external push from a nearby galaxy flyby. Over time, even if they spread out in space, they can retain a memory of that disturbance in their velocities and orbital properties, clumping together in what we call phase space.
Phase space, so that's the map of where stars are and how they're moving.
You got it. Position and velocity combined. When stars share a history, they tend to cluster together in this phase space, even if they look scattered across the sky to us.
Okay, so the mission here, armed with Gaia's precise data, is to figure out which of these origins explains a particular stream we see.
Precisely.
Is it accreted debris, a resonant feature, a dissolving cluster, or, something else entirely?
Exactly, because identifying the origin of these local streams provides crucial insight into the fundamental processes that built and shaped our Milky Way over cosmic time.
And helps us understand the different populations of stars that call it home.
Couldn't have said it better.
Okay, armed with that understanding, let's grab the first specific example, the famous Arcturus stream. This really shows how Gaia changed the game, right?
It really does. This group was first spotted way back in 1971 by Olin Egan.
Right.
He found an overdensity of stars, about 50 of them, all sharing a similar velocity component in the direction of galactic rotation, what we call the V velocity.
V velocity, got it.
And it was around megach 100 kilometers per second, which is, pretty fast against the main flow. And yes, the very bright star Arcturus itself was among them.
And Egan's first thought was another evaporating cluster.
Yep. That was the initial hypothesis. But today, that idea is heavily, heavily disfavored for the Arcturus stream.
Okay, why? Why is the dissolving cluster idea out for this one?
The main piece of evidence against it is the chemistry of the stars, their composition.
Ah, the metallicity.
Exactly. Metallicity, the abundance of elements heavier than hydrogen and helium. If a group of stars were all born together in a single cluster, you'd expect them to have a very similar chemical makeup.
Like they all came from the same batch of cosmic dough.
That's a great analogy. The recipe should be the same.
But for the Arcturus stream stars, the recipe, it varies.
It does. The stars in the Arcturus stream show a notable spread in their chemical abundances and their metallicity. That kind of heterogeneity isn't expected from stars that formed as a single coherent group in one place at one time.
Fascinating. So, okay, cluster idea is shaky. Before Gaia really nailed it down, what were the other leading ideas for Arcturus?
Well, there was a pretty significant debate happening. One strong contender, supported by studies looking at earlier, less precise data, was that it originated from an accreted satellite galaxy.
Another galactic meal remnant?
Possibly. This was based on properties like the stars having relatively low angular momentum.
Meaning their orbits don't swing out as far.
Right, and low metallicity, which you might expect from a smaller, less chemically evolved galaxy. Plus, they had similar apocenters the furthest point they reach in their orbits.
Okay, so accreted galaxy was one possibility.
Yeah.
But there were others.
Yes. Some researchers felt you couldn't rule out it being a resonance feature linked to the Milky Way's central bar, that gravitational influence trapping stars.
Like the Hercules stream, maybe.
Sort of, yeah, that kind of mechanism. And then another idea was that it might simply be an unrelaxed disk population.
Unrelaxed. Meaning?
Stars already in the Milky Way's main disk that were stirred up by some major disturbance, maybe a galactic merger event, say, around 1.9 billion years ago.
Yeah.
And they were still kind of settling down dynamically, still showing the effects of that ancient shakeup.
So dissolving cluster, mostly ruled out, accreted galaxy, bar resonance, or just a disturbed disk population. 3 very different possibilities on the table.
Yep, it was a bit of a puzzle.
How did Gaia data, specifically, help cut through that uncertainty?
A really landmark study in 2019 by Kushnorek and Bensby took Gaia DR2 data, that's data release 2.
A massive data set.
Huge, and they really dug into this question. They analyzed over 5.8 million stars within about 5 kiloparsecs of the sun.
5 kiloparsecs, that's what, about 16,000 light years? Okay, that's a big chunk of space.
It is, and they used Gaia's incredible precision not just to look at simple positions and velocities, but to calculate more fundamental properties that describe a star's orbit through the galaxy's gravitational field.
Okay.
Properties like angular momentum, which we mentioned, relates to how widely a star orbits, and crucially, quantities called actions.
Actions. Tell me more about why those are so important. They sound fundamental.
They really are. Actions are derived from a star's motion and position in the galaxy's gravitational field, but the key thing about them is that they are conserved, at least in a smooth, unchanging potential. They don't change as the star moves along its orbit.
Oh, okay.
Think of them as a permanent tag on a star's orbit, a signature that reveals its true family history and how it was influenced by the galaxy's structure and past events. Stars that share a common origin or have been subjected to the same dynamic processes will tend to have similar actions.
Okay, so if simple speed and direction change constantly along the orbit, actions are like the unchanging DNA of a star's path through the galaxy.
That's a great way to put it. They're incredibly powerful for finding groups of stars that belong together dynamically.
And need Gaia for this because...
Because to calculate these actions accurately, you need very precise measurements of a star's distance, how it moves across the sky, that's proper motion, how it moves towards or away from us radial velocity.
Right.
Gaia provides the first two with unprecedented accuracy. Then researchers combine that with ground-based spectroscopic surveys like APG or Gaia to get the radial velocities and the chemical compositions.
Got it. So what did the Kushneruk and Bensby study find when they applied this powerful Gaia analysis to the Arcturus stream area?
Well, they clearly identified the Arcturus stream as a distinct structure in maps of stellar velocity and angular momentum. No question it was there.
Yep.
Its properties confirmed it as a high-velocity, low angular momentum feature. And when they looked at the chemistry using that spectroscopic data,
Yeah.
they found its stars have a metallicity distribution that looks very similar to the Milky Way's thick disk population.
The thick disk. That's an older, kind of puffier layer of stars in our galaxy's disk, right?
Yeah.
Compared to the thin disk where the sun is.
Exactly. Generally older and dynamically hotter stars. They also found the stream extends further above and below the galactic plane than structures typically driven by the galactic bar, like the Hercules stream we mentioned.
Okay, so low angular momentum, thick disk chemistry extends far from the plane. How did those findings settle the pre-Gaia debate?
Well, their conclusion was quite strong. These observed properties, the combination of kinematics, the orbital characteristics, and especially the chemical makeup resembling the thick disk, are distinctly different from what you would expect if the stream was purely a resonant feature of the galactic bar.
So probably not the bar's influence then.
Probably not primarily the bar's influence, yeah. Instead, the study strongly suggested that the Arcturus stream is likely part of a phase space wave or ripple.
A wave.
Yeah, like a lingering effect caused by an ancient merger event, the impact of another galaxy hitting or passing through the Milky Way's disk billions of years ago, stirring it up.
Wow. So Gaia data doesn't just refine the picture. It points pretty convincingly to an ancient merger origin, or at least a major ancient disturbance.
That seems to be the leading theory now, yeah.
And effectively rules out the simple dissolving cluster idea for Arcturus.
That's right. And it gives a whole new perspective on a star that's been, visible to humans for millennia.
It truly does. There's a quote from an earlier paper by Navarro and colleagues back in 2004, which the sources mentioned, that really captures this.
Oh, yeah, I remember that one.
It is oddly gratifying to think of stars visible to the naked eye, such as Arcturus, as silent night sky witnesses of the merging history of the Milky Way.
It's quite poetic, isn't it? It connects our local view of the night sky to the truly colossal events that built our galaxy.
Absolutely. Okay, let's shift gears and look at the second example.
Yeah.
The HR 1614 group. Did Gaia rewrite its story too?
Absolutely, but maybe in a different, perhaps even more complex way. This is another group first identified by Egan back in 1978. He found about 40 stars, including the star HR 1614 itself, all sharing a mean rotational velocity v of around negative 60 kilometers per second.
So also moving together, but perhaps not quite as dynamically hot as the Arcturus stream, different velocity.
That's right, a different bulk motion. And Egan initially classified this group, like Arcturus, as an old dissolving open cluster.
It's an initial idea.
Yep. He noted that its stars appeared to have higher metallicity than our sun, and he estimated an age of about 5 billion years.
And there was some follow-up work even before Gaia, using Hipparcos data.
Yes. Feltzing and Holmberg in 2000 used data from the Hipparcos mission, which was Gaia's predecessor, though much less precise.
Right.
They also concluded that HR 1614 was likely a disrupting, metal-rich, open cluster, although their age estimate was younger, closer to maybe 2 billion years. So the pre-Gaia consensus definitely leaned towards the dissolving cluster idea for this one.
Okay, so enter the Gaia study. How did Kushneruk and colleagues revisit HR 1614 using Gaia DR2? This is a 2020 study, right?
That's right, 2020. They applied similar techniques as they did for Arcturus to the HR 1614 group, again using Gaia DR2, and combined it with spectroscopic data from Apogee and Gaia.
To get the chemistry and radio velocity.
Exactly, to refine which stars were truly members and get their detailed kinematics and chemistry.
And what did their analysis reveal about this group? Was it also not a cluster?
Well, kinematically in velocity space, this group doesn't show the simple, clear shape you might expect from a dissolving cluster or a simple resonant feature. It didn't form a clear arch of constant energy, for example, and its structure looked somewhat tilted in velocity space. But the strongest evidence came, again, from the properties of the member stars themselves.
The chemistry and ages. Let me guess.
You guessed it. They found that the stars identified as belonging to the HR 1614 group exhibit a wide range of metallicities, a noticeable spread in their estimated ages, and diversity in other chemical abundances, too.
Ah, so just like with Arcturus, that diversity in chemical recipes and birth times, it really suggests they didn't all come from the same single batch in one cluster.
Correct. If they were all born together in a single open cluster, you'd expect much more uniform ages and chemical compositions. Based on this wide range of properties, combined with the complex kinematic structure, the study concluded that HR 1614 is definitively not a simple dissolving open cluster.
Okay, so the cluster idea is out for HR 1614 too. Does it look like debris from an accreted galaxy then? Like maybe Arcturus?
Well, the study also found that its properties don't strongly align with a single, coherent, accreted population from an external galaxy either.
Huh.
The characteristics of the stars and their orbits, they just don't quite fit the typical signatures of merger debris that we see elsewhere in the halo or disk.
So if it's neither a simple dissolving cluster nor straightforward accreted debris, what is the explanation for why these stars are moving together? Sounds like it has a really complex origin.
It really does. This one seems trickier. The evidence points to the HR 1614 group being best explained by a combination of several different dynamic mechanisms happening within the Milky Way's disk.
A combination, like what?
The study suggests it's likely shaped by influences including resonances with the galactic bar and spiral structure,
Okay, so internal dynamics.
along with phase mixing caused by things like dissolving spiral arms, or perhaps even phase mixing triggered by an external disturbance. Maybe even the same ancient merger event potentially linked to Arcturus, but affecting stars in a different region or a different way.
Wow, that paints a picture of the Milky Way's disk being constantly stirred up and influenced by multiple processes simultaneously. This group is like a messy result of all of that complex galactic churning.
That seems to be the current understanding based on the detailed Gaia data. It's a far more intricate story than just a simple cluster fading away. It highlights the ongoing, complex dance of stars within our galaxy.
These two examples, Arcturus and HR 1614, they really drive home how Gaia has revolutionized our ability to understand these stellar groupings right near the sun.
Absolutely.
And they're just a small sample of what's being discovered, right?
Yeah.
The sources mention even more recent work building on this using the latest Gaia data.
Yes, there's a significant study by Lucchini and colleagues in 2023 using the most recent Gaia data release, DR3.
DR3 even better data.
Exactly. And they've even developed a new open source tool called MG-Wave, which is quite sophisticated. It can find not only over densities, concentrations of stars moving together, like the streams we've discussed, but also under densities.
Under densities like gaps, absences of stars moving in a certain way.
Precisely. Those gaps can also be powerful clues about the dynamic history of the galaxy, maybe showing where stars have been swept out of a certain orbital path by resonances or other effects.
That's clever. So what did they find with this new tool in DR3?
Applying this tool to Gaia DR3, which contains even more stars and even better measurements than DR2, they detected a total of 47 distinct kinematic groups.
47.
Yeah.
Did they confirm the ones we already knew about, like Arcturus and HR 1614?
Yes, they successfully recovered most of the previously known moving groups, which is great. It validates their method. But they also identified 3 additional significant candidates for entirely new groups.
3 new ones just from the latest data release. That's really exciting. Where are they?
It is. Interestingly, one of these new candidates was found surprisingly within the previously identified Arcturus stream area.
Within Arcturus, so there might be substructure there.
It suggests there might be even more intricate substructure within that larger feature than we first thought, maybe multiple components mixed together. The other two new candidates were in different regions of velocity space that hadn't shown much evidence of kinematic substructure at those specific velocities before.
And these studies are now pushing further out into the galaxy too, mapping dynamics beyond our immediate neighborhood.
Exactly. These systematic searches are now extending further into the galactic disk, reaching out to maybe 10 kiloparsecs from the galactic center. That's over 30,000 light years. It allows us to map these dynamic structures over a much larger volume of the galaxy.
It seems the key takeaway here is just undeniable. Using Gaia's incredible ability to measure the precise motions and properties of stars right here near the sun is an astonishingly powerful way to untangle the complex structure and, the billions of years long history of our Milky Way.
Absolutely. With each new Gaia data release providing better and more numerous measurements, we're not only refining our understanding of known structures like Arcturus and HR 1614, but continuously peeling back layers of complexity and discovering entirely new ones. Our local neighborhood holds this incredible wealth of information about the entire galaxy's past.
So we've taken a deep dive today into how Gaia data is truly revealing the complex, dynamic nature of star streams, like the Arcturus stream and the HR 1614 group. We've seen how they're often not just as simple evaporating clusters,
Definitely not always simple.
but intricate structures with origins tied to the Milky Way's sometimes violent history of past mergers, and the ongoing churning effects of its internal dynamics like gravitational resonances.
And these streams, they aren't just abstract features in astronomical catalogs. They're right here in our galactic backyard, part of the very fabric of our home galaxy, shaped by billions of years of cosmic evolution.
And that brings us back to where we started. Think about Arcturus, that bright reddish star you might see tonight if you look up. Now, consider that it's not just a single point of light traveling randomly.
Yeah.
It's part of a vast, ancient wave of stars, a silent witness to colossal events that shaped the Milky Way billions of years ago, perhaps the disruptive impact of another galaxy, or the long-term stirring effects of our own galaxy structure.
It really makes you wonder, doesn't it? What other cosmic histories, what other echoes of galactic evolution are written in the precise motions of the stars above us, just waiting for us to decode with better data and, well, clever tools?